So let's start looking at the integral test. So we'll have our quiz on Monday over 9.2. So the integral test wraps back around again on one of the last sections we did in the second unit. And one of the things you learned at the end of the second unit was how to evaluate an improper integral. And when you evaluate an improper integral, that was when you saw like infinity in as an indice on the integral, right? So they look like definite integrals, and then sometimes improper integrals didn't have infinity at all. They had a number, but if you actually looked at the original function you were integrating, you would see that that number didn't work in the function. So for example, if we wanted to integrate 1 over x from 0 to 1, right? Well, 0 can't be plugged into that function. And when you try to plug 0 into that function, right, what you would see is you have a vertical asymptote there. So with 1 over 0, when you're at 0, the thing that makes the integral improper is the 0 value, and it's creating a vertical tail, okay? So when you look at an equation where we evaluate to infinity and you graph that function, you'll see it has a horizontal tail, okay? So this concept of trying to grab all the area under that tail is a very, very important idea, and it's actually quite useful. Can anybody think of where you would want to get the area of a tail of something? Everybody taking a stat class, right? The area under the curve in statistics is probability. So if you want to know what's happening on the upper end of a distribution, like 90% and above, you have to really grab all the area to the tail. So in statistics, when you derive the density function for area under the curve, almost all distributions have a tail, and so we do improper integrals all the time. They're really, really useful. So what we did with an improper integral is we said, well, we're going to calculate this area, and if we got a finite number out of the integral, then we said that the integral converged, meaning that as the tail is formed, right, the heights of the tail are going to 0, right? And if you can actually capture the area, it means the tail's going to 0 very quickly, and by the time all the terms just become height 0, we've already grabbed finite area. If the area under the curve turned out to be infinity, it means the tail was too fat, and it was going to 0 too slowly, and by the time we got to the 0 terms, we had already grabbed infinity under the curve. So one of the things that's nice about that is we can actually apply this logic to series. And we can actually see, well, if the integral diverges, the series will also diverge and vice versa. So let's look at the criteria you need to even apply the integral test to a series. So if you have a function f of x that is positive, continuous, and decreasing, for all x greater than or equal to 1, and you have a sequence that could be written as a function of n. So what we're saying here is when you're looking at the structure of the sequence, if it looks like something that if you changed all the n's to x's would just be a nice continuous function that fits this criteria, you can apply the integral test. All right? So what we're saying is that the series and the integral will behave the same way. So either they will both converge or they'll both diverge. And we're going to do a couple of examples with this, and I'm going to walk you through the mechanics of evaluating an improper integral. Now, it doesn't mean for all the examples we're going to do that there aren't other tests we could apply later that we learn, but this is just another good thing to have in your back pocket if you're pretty strong at integrating and you just can't think of another way to do the problem. All right? So let's look at the series from 1 to infinity of n over n squared plus 1. So the first thing that I want to check for is that the limit of the nth term is 0, right? So we know that these values are collapsing down to 0 as n gets to infinity. So I know these are decreasing, right? I can also look at this function or this series, and I can tell that if I replace my n's with x's, that is going to be a continuous function from 1 to infinity, right? And as a matter of fact, the domain of this function would be all reals, because the only issue you would have is getting 0 in the denominator, and since n squared, you're never going to have that -1 to ever make the denominator 0. So we know this thing works for all values of x between 1 and infinity. We also can tell by looking at this, since the values of n that are going to go in are between 1 and infinity, this thing's always positive. So it meets the criteria to apply the integral test. So let's let f of x be x over x squared plus 1. And just to give you some context here, I'm going to draw a picture what this function looks like. So if we integrate from 1 to infinity, the integral is trying to grab all that area. So this is what I mean, you'll always have a tail involved. It'll either be a horizontal or a vertical tail. Now when you're applying the integral test for series, it'll always be a horizontal tail, because we're talking about always taking these out to infinity. All right? So if we set up the integral, now one other thing I want to mention. Generally, we're saying 1 to infinity because we default when we write series like this from 1 to infinity, okay? But that doesn't mean it always has to be 1 to infinity. Sometimes we look at a sequence from 2 or 3. So what you want to make sure when you set your integral up is that the bounds on the sequence match the bounds on the integral, okay? So this is a u substitution, and if I let the denominator be u, then du is 2x dx. So the thing I need to check for back in the function is, do I have that extra x in the numerator? And I do. So what you want to do when you're doing your u sub is you want to solve this equation for the things you already have in the integral. So I have the x, I have the dx, so du over 2 will replace x dx. And so u substitution is like translating in a different language, right? We're literally going to translate the integral into a different variable. So what you want to do here is do not write the new bounds, because it is implied in an integral the dx is saying this is the variable, and so we don't write it out because it's cumbersome, but what this is saying is x equals 1, x equals infinity. When you switch to u, the bounds aren't that anymore. Now when we're doing improper integrals, this is one of the rare instances where I actually say don't change the bounds on u. You're just going to make life more complicated. So what we want to do when we switch to u is we want to treat it as an indefinite integral. Just take the bounds away. The 1/2 for the du, I'm just going to pull out front. So all I have to integrate is 1 over u du. The 1/2 is a constant, and the antiderivative of 1 over u is the natural log of u. Then we're going to put it back in variable x. And when we go back to evaluate our bounds, we're not going to plug infinity in because that's not something we do. We're going to replace the part of the integral that was improper with the value b. So the standard notation, since when you see a standard integral, we say it's evaluated from a to b. If the top thing is the thing that's bothering you, we put that as a b. If it's the bottom value that's bothering you, then we usually just put an a there, right? So the a and b just mean lower upper, because when we write an interval generically in math, we usually just say from a to b, okay? So now I'm going to plug in these bounds, because we don't actually plug infinity into an equation. That really irks me when people do that. And I can drop the absolute value signs because these values are all positive. So I'm going to have the natural log of b squared plus 1 minus 1/2 the natural log of 2. So the next step when you're evaluating an improper integral, once you've replaced it for b is we now say, well, what was b taking the place of? So in this case, b was taking the place of infinity. So then we use a limit to see how does our answer behave as b is going to infinity. So the limit as b goes to infinity of 1/2 times the natural log of b squared plus 1 minus the natural log of 1/2. So does anybody remember what natural log does as you make the inputs go to infinity? No? No one ever does. Huh? Doesn't go to 0. It actually goes to infinity. So this is the graph of natural log of x. So as the values inside the log get bigger and bigger and bigger, the graph approaches infinity. It just approaches infinity very slowly. So this limit is equal to infinity. So therefore the sequence, or the series, excuse me, diverges. And so that's what we're saying with this test. The integral and the series will behave the same way. So if the integral diverges, you know the series diverges and vice versa. So what do we look for when we want to apply this test? Well, we definitely need the nth term to go to 0. So what we're saying here is that if the limit as n goes to infinity of a of n equals 0, it might converge. So therefore we need to proceed with the test. Right? If it fails that first test, we just stop it and we know we're done right there. Also, if the limit of the nth term is not going to 0, chances are this function may or may not be decreasing and we might have a problem that way too. But if the limit fails to go to 0, the series diverges because that's the whole point that we're checking for. Right? Also, you want to look for expressions that make sense as a continuous function of x. So if you have any factorials, can't do it, right? You may want to make sure that it's something that can actually be rewritten as a continuous function. All right, so I want to look at another example that will kind of show us a little bit further what's going on. So before we look at this next example, pay attention to the form of this equation right here, because the next one we're going to do is going to look very similar to this, but it's going to behave in a different way. So the only difference between this series and the one we just looked at was the last one had an n in the numerator. This just has a 1 in the numerator. So one of the things that happens when we're looking at these improper integrals is the faster something goes to 0, the better chance you have of convergence, because that means the tail is thinner and those terms are going to get to 0 quicker. So it's really the stuff in the denominator that's driving kind of the speed it's going to get to 0, right? Because if you blow a denominator up to infinity, everything's going to end up at 0 eventually. What's happening in this guy versus the previous one was in the previous one, we had an n in the numerator. And that n in the numerator was kind of slowing it down because every time you would make the denominator bigger, you still had a constant in the numerator. And that constant in the numerator was growing as well. In this case, the numerator is just staying 1. So as you make the denominator bigger and bigger and bigger, it's actually going to reach 0 much quicker. Okay? So this is actually a known derivative. Does anybody recognize it? If you change the n to an x, it's the derivative of a function. It's an important one. You should know it, right? It's going to be arctan. So the fact that I see this as arctan means the integral test is perfect because I can anti-differentiate it really quickly. So if we set up the integral, well, I know that this is going to be arc tan of x, and we'll evaluate it from 1 to b. So this is going to be arctan of b minus arctan of 1, and this is what we need to take the limit of as b goes to infinity. So evaluating the limit as b goes to infinity of arctan, it's kind of like doing the limit of natural log of x. So it really helps if you know what the graph looks like. So tangent, right, when we graph it, it looks like an S, right, and it repeats and repeats and repeats, and it's got vertical asymptotes at every multiple of pi over 2, okay? So when you take the inverse of tangent, what it does is it flips the graph on its side, and the horizontal or vertical asymptotes on the original graph become horizontal asymptotes on the new graph. Also, we limit arctan to only going vertically between negative pi over 2 and pi over 2 because otherwise we would have the other s's, for lack of a better word, right, would stack on top and bottom, and then it would cease to be a function because it would fail the vertical line test. So remember, when we flip or do the inverse of a lot of trig functions, we restrict their domain so that they're invertible. So when you graph arctan, it looks like this. So as the values inside the function get bigger and bigger and bigger, the limit to infinity is pi over 2. If you evaluated the limit to negative infinity of the same function, you would get negative pi over 2. So the first piece of this is just pi over 2. Arctan of 1, remember with inverse trig functions, you put the point in and the angles come out. So if arctan is, if tangent equals 1, that means sine and cosine are the same, and that occurs at 45 degrees or pi over 4. So pi over 2 minus pi over 4 is pi over 4. So the integral converges, which means the series converges. All right. So I want to dig into this one just a little deeper to kind of show you kind of what's actually happening with the integral test. So this is the function we just integrated. The graph looks a lot like the graph of the previous function. It's just approaching 0 much, much quicker. And if we go back and remember when we first started learning integrals, the way that we did it was we made rectangles and we summed the rectangles to get an idea of what the integral was going to be. The series, however, is only returning the vertical heights at each of these values. So in the series, when you plug in n equals 1, the height of this y value is the first number that comes out of the series. At 2, right, 3, 4, right, and we'll stop at 5. So if you were to sum the heights of those lines, that's the series, okay? But when you're summing an integral, you're actually accounting for all the stuff in between as well. So when we did this with rectangles, we looked at the left-hand sum and we looked at the right-hand sum. So if we look at the left-hand sum, the way that worked was you would go to the left side of the very first number you were integrating, you would measure to the top of the function, and you would draw a rectangle equal to the width of the delta x you chose. So the left-hand sum of a decreasing function is going to give you an overestimate. It's grabbing more area than we need from the curve. But if you look at the right-hand sum, you would start on the right side, right, and draw your rectangles this way, and we would see, well, that would give us an underestimate. So when you have a decreasing function, the true area, which is what the integral returns, is somewhere between the left-hand sum and the right-hand sum. So if it's a decreasing function, the left-hand sum is bigger. If we had an increasing function, that inequality would be reversed. You'd see that the right-hand sum would give you the overestimate. So if we look at what those values actually are, one of the things that's a little frustrating when you start looking at series, it's very unsatisfying, is the first series we show you are the geometric series, which you can actually sum and get the true sum. Then we show you a telescoping series, which you can actually sum and get a sum. And then after that, pretty much all we can talk about is, well, we know the sum exists. That's what converging means, right? But we don't actually know what it is, okay? So when you're doing the integral test, do not fall into the trap that the area under the curve is the sum of the series, okay? It's somewhere in the ballpark of the sum of the series, but is not the actual sum. And so you can see that when you look at rectangles of width 1. Okay, so the reason that you always want to pick width 1 is the series only accepts whole number integers. So we always want to make sure those rectangles have width 1. So if you look at the left-hand sum here, when I plug 1 into my original function, I'm going to get 1/2. But if you're thinking about it in terms of area, the height of the rectangle is 1/2, but the width is 1, so it just still returns 1/2. So you're going to get 1/2 plus 1/5 plus 1/10, right? And it would sum like that. If you start and look at the right-hand sum, well, then all these values shift over by 1 because we would start at 2 to measure the height of our rectangle. So this would be 1/5 plus 1/10 plus 1/17. So which one of those, it doesn't always work out to be this way, but which one of those is the actual series we're summing? Just go back and plug in the first number in the series and see what you get.
Left hand.
The left hand, right? So the series starts counting at 1, 2, 3, 4. So in this particular example, the left-hand sum is in fact the sum of the series. Now, we would still have to do this out to infinity. So if you look at this inequality, pi over 4 is less than or equal to the true sum of the series. So it's possible that the sum's a little bit more than pi over 4. It could actually work out to be equal to pi over 4. But the point of this is, do not assume that the area under the curve is actually returning the exact sum. And if you look at the left-hand sum was an overestimate. So it absolutely will be bigger than pi over 4. But it does still exist, and it is a finite number, right? So you're just going to have to get used to this point when we're looking at series. That's just a little unsatisfying. It always feels like all the problems are incomplete. All right, any questions on that? Yeah.
This might be me misremembering how sums work.
Mm-hmm.
Isn't the right-hand sum the one starting at 1/2?
The
left-hand sum the other one?
left-hand one, no, because the left-hand sum, you plug in 1, and if you look at the structure of the equation, it's 1 over 1 plus 1, which is 1/2. See? Like if you go back to the series.
Yeah, but I'm still, it's looking at the graph.
So the left-hand sum and the right-hand sum, you start the rectangle on the left side of the interval. On the right-hand sums, you start the rectangles on the right side of the interval. But remember, they're reversed for increasing and decreasing functions. So the left-hand sum's giving us the overestimate, on a decreasing function, and the right-hand sum's giving us the underestimate. So unless I've got my left and right wrong, the left is here, you go up to the top and measure over, and that height is 1/2.
The terminology is very confusing considering you go right, but it's a left-hand side.
Well, the left hand means you measure the height from the left. So you start on the left side of the rectangle and you go up to the graph, and that's where you draw the rectangle from. The right-hand sum means you measure the height of the rectangle from the right side of the rectangle. That's what that means.
Okay.
Yeah, and if you go back and look, the leftmost endpoint of your interval is the first value you plug in. When you're talking about right-hand sums, the B of your interval gets plugged into the function. Yeah.
Like on the test, for like these kind of functions,
Mm-hmm.
would we also need to find the left and the right hand sums?
No, you're not. I'm only doing this as an example to just kind of explain why the integral test works and just kind of remind you about like what does an integral have to do with a summation, and you're both summing. It's just integral sum area. The sums are summing the actual integer values. And so I'm just trying to show you guys that like even though we get an answer out of the integral, why it is not the actual sum of the series. Okay, but no, on the integral, if we got a problem like this on the exam, right, that's all you need. You just have to evaluate it, get an answer, and tell me what the answer means, right? And on the previous one, if you notice, when we got infinity, we just stopped. We were done. It diverged, right? So I'm just trying to kind of explain a little bit why the integral and the sum will behave the same way, okay? So there's two ways we add things up in math, right? And the stat person in me, we would call series discrete functions because you only plug in whole number values and you don't return integer values, but you get whole number values and you're summing up a list of things. A function is continuous because it allows every value of x to be plugged in. So when we're summing continuous things, we use integrals, right? When we're summing finite or discrete things, we use summation because it's a discrete list of things, okay? So stat people kind of use discrete and continuous a little bit differently than pure math people. All right, so there's another really awesome series, right? When we see geometric, it's really easy to work with. There's another one that's extremely useful that we need to look at, and every time you recognize one, you should get excited because they're super easy to tell if they converge or diverge, right? You just look at them and tell, right? And those are the p-series and the harmonic series. So we're going to write down what they are, and then I'm going to show why they're true, okay? So the first one, right, a p-series takes the form of 1 over n to the p, okay? P is a constant number. So it will typically be, well, it will always be given in the series. So it could be 1 over n squared, 1 over n cubed, something like that. But it will stand for a constant number, right? So if you sum this up, remember n is the variable, not p. So when you look at the first couple of terms of this, right, you'll have 1 over 1 to the p, 1 over 2 to the p, 1 over 3 to the p, and etc. These series, for values of p that are greater than 1, converge. However, if we let p equal 1, then we just have the series 1 over n. And 1 over n, right, is 1 over 1, 1 over 2, 1 over 3. And so a p-series where p equals 1 actually diverges, and it even has a special name, and we call it the harmonic series. So if you recognize a harmonic series and you just say, that's the harmonic series, it diverges, that's okay, right? Because once we prove it in class why that's true. If you recognize a p-series and you say that's a p-series and give me the p-value and then state whether it converges or diverges, that's okay as well. So the reason that these series are in this particular section is that you prove the convergence and divergence of p-series by using the integral test. So on the exam, if I simply say, does the series converge or diverge, and you recognize a p-series, and you state that, that's fine. But if I ask you, show me why this particular P series converges or diverges, then you have to apply the integral test. That's how you show it. So I'm not going to I'm going to show you this proof. I'm not going to ask you to regurgitate the proof. We just need to understand why these work, because they're going to come up a lot later. But if I give you, for example, 1 over n squared, I will actually give you at a constant p value, and you just apply the integral test. And they're very easy to integrate. But I want to see if you know that. So make sure that, hint, 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 when you're studying for the exam, that you know how to do the integral test on a p series to show me what's happening. Yes? Okay. So let's look at the proof of this. It's actually pretty intuitive. And then when we're done with this, we'll call it. It's Friday for me too, y'all. All right. So we have a series, right, of this form. And we're going to compare it to the function of 1 over x to the p. This function is continuous. It's decreasing, right, for all x greater than or equal to 1. And so it's going to meet the conditions for the integral test. So we're assuming here that p has to be greater than 0. What would happen to this if p was negative? Like if I had negative 2 as p? It would go to the numerator and become positive. So if you see this series and p's in the denominator and it's a negative value, it's technically, if I had 1 over n to the negative 2, that's technically n squared, and those limits will all go to infinity. So those things will all diverge. So we have to assume that our p values in the denominator are positive values, right? So if we set up the integral from 1 to infinity of 1 over x to the p dx, the first thing I want to do is rewrite it as x to the negative p, so then I can just apply the power rule when I'm integrating. It's a lot easier. So when we integrate, right, we add 1 to the exponent, and then we divide by that exponent. And we're going to evaluate this from 1 to b. Before I plug in my values, however, I know that it's going to still be in the denominator. So I'm going to rewrite this a little bit to make it look a little cleaner. So remember, you can reverse the order of subtraction. And so I'm going to rewrite the denominator as 1 minus p. That's the same thing. It's just changing the order. And then I'm allowed to move my x to the p, negative p plus 1 in the denominator. But when you cross the fraction bar, you multiply the exponent by negative 1. So this now becomes p to the x minus 1. And the reason I want it back in the denominator, it's easier for me to evaluate the limit. I can see when it's going to 0 or not because we don't have real numbers here to deal with. So when I evaluate this, I'm going to get 1 over 1 minus p as the constant. I'm just going to pull that out front. And I have 1 over b to the p minus 1 minus 1. Because when you plug 1 in, 1 raised to any power should just come back as itself. So now I have to evaluate the limit of this, but I'm going to have to do this in cases because I have a couple options for p. The only condition I set at the beginning of the proof was that p had to be positive. So let's look at a couple of cases, right? If the value of p is between 0 and 1, then the limit as n goes to infinity of 1 over 1 minus p times 1 over b to the p minus 1 minus 1, right? So in order to see this, let's just, for example, let's pick an easy value between 0 and 1. So let's pick p as 1/2. What happens to the exponent of b if p is 1/2? It becomes negative 1/2, right? So any value less than 1, if you subtract 1 from it, it becomes negative, which then pushes it back up in the numerator, and we know that limit would be infinity. So right? You can actually see this with real numbers if you let p equal a half. If p is greater than 1, well, now when we evaluate the limit, if you have a number bigger than 1 and you subtract 1 from it, it's still a positive value, so the b stays in the denominator, and that means the limit of this term goes to 0, but we're still left with our constants, so it's -1 times 1 minus p. So it doesn't matter that it's a negative number, it just matters that it exists, and so we would conclude that these series converge. Now, I left off a number here. We didn't talk about what happens if p equals 1. Well, if p equals 1, we actually have to set up the integral again because the antiderivative of that is different. So if p equals 1, the integral of 1 to infinity of 1 over x has a completely different antiderivative. And so hopefully by now you guys all know that's ln of x. So we get ln of b minus ln of 1, which is 0. And we just saw that the limit of the natural log of something as the inside of it goes to infinity is also infinity. So the punchline is, if you see a p-series, right, if the value's between 0 and 1, it diverges, and if the value's bigger than 1, it converges. So now we can say any p greater than 0 or less than or equal to 1, those series diverge, but any p-value greater than 1, those series converge. You have a question?
Could you slide the paper down?
Yeah, sure. Yeah, there you go. Do you have a question? Yeah, what's up?
On the first example we did for the integral test,
Mm-hmm.
you said that the limit of the n over n squared plus 1 equals 0.
The limit of n over n squared plus 1, yes, equals 0.
Does that mean like the series or the sequence equals 0?
That means the sequence would converge to 0, yes.
So if that were the case, doesn't that mean like can we just say that means the series never converges?
No, remember, what we said is in order for any series to converge, the sequence has to go to 0. But a sequence going to a 0 is not a guarantee of convergence. That just means keep going with the problem. If that limit did not go to 0, it automatically diverges and we shut the problem down. So that's what we said when I said the, here it is, right? This was the, I'll put this back in a second. This was the nth term test for convergence. If the series converged, then the limit had to be 0. If the limit is non-zero, then you know the series diverged. So every single one of these functions that that we even attempt to do one of these tests on, those limits all do go to 0, right? That just means keep going. So the harmonic series has a limit that goes to 0, but the harmonic series diverged, right? 1 over the square root of n, the limit of that goes to 0, but that's a p-series where p is 1/2, and we just proved that that's going to diverge, okay? So it's not a guarantee of convergence, it just means you have a shot. All right, any other questions?